This is a final run through of the key topics for the foundation tier of AQA GCSE Combined Science Physics Paper 2 in 2022. In other words, I've missed out the forces and elasticity section because that's in the not assessed section of the advanced information, and I've also missed out all of the required practicals apart from number 21, which is the only one that was named in that advanced information. Each one of the major topics is shown on a green slide so that you know that those are extra important, but I have included all of the other topics that aren't mentioned at all on lilac slides because they can still come up as low tariff questions. I also won't be going through all of the equations in depth because you will have the equation sheet for the exam. After 6 exams, hopefully you know all of this, but just for the final time, it's really important that you're writing in black and staying inside the boxes because your exam is going to be scanned. Watch out for any sneaky units, particularly if you're thinking about masses or distances, which could be in centimetres instead, and you might need to convert. Feel free to use bullet points. They're going to make your life easier and your examiner's life, and there are no marks at all for writing in full sentences. If you're asked to evaluate, then remember to compare and write a conclusion, and make sure that any methods you write have a logical flow to them and could be followed by somebody who hadn't done the practical before. Make sure you're confident identifying the variables for any practical activity and that you know the difference between repeatable and reproducible data. The resolution of your equipment is the smallest difference in data that it can identify, and we like computerised methods for collecting data because they're accurate, rapid and sensitive. If you have to transfer some data from a table onto a graph, then make sure that you are including all of the data points, even if there is one that goes at the origin at 0, 0. And remember that lines of best fit don't need to be straight lines, whatever your maths teacher has told you about GCSE maths. Hopefully you're already really aware that in the physics papers in particular, up to 30% of the marks are going to be for assessing mathematical skills. So there is a full list in chapter 9 of the specification, but these are the key skills that you could be assessed on in this paper. So it's worth having a quick look and making sure, do you know what all of these things mean? And also as you're going through the paper, highlighting where you're asked to do one of these. We really commonly see a situation where a candidate is asked to, for instance, give their answer to a certain number of significant figures or answer in standard form, and maybe they know how to do that, but by the time they've done the calculation, they forget that they've been asked to give the answer in that format. So I would just make it really explicitly clear to yourself. As you know, in 2022 you are going to be given a copy of the equation sheet for the physics exam, but don't forget that this only has each equation in one format, so you may still need to rearrange it in order to answer the questions. It also doesn't tell you anything about the units for any of the quantities, so it's worth spending maybe a minute at the start of the exam quickly jotting these down before you forget them. You should know that all forces, including weight, are measured in newtons, and that masses must be measured in kilograms. It's very likely that the exam board could give you a question where they give you the mass in grams and you need to divide by 1,000 in order to convert it. Now, if you have that first equation there, we can rearrange it to make it weight over mass is GFS. And so if we then put the units in and make it newtons over kilograms, then we have the units for GFS as newtons per kilogram. Work done is a type of energy, so it's in joules, and distance must be measured in meters. Again, it's very likely that the exam board give you a sneaky question where they give you a distance in centimeters or kilometers instead, and you're expected to convert before you complete the calculation. A spring constant, again, we can work out from the other units. So we can rearrange this equation to have force over extension is spring constant, and that therefore is newtons divided by meters. So newtons per meter is the unit there. Speed and velocity should be measured in meters per second and time in seconds. Acceleration is in meters per second squared. And remember that squared is part of the unit, so it's not saying that you need to do any squaring in your calculations. In physics, we divide quantities into scalar quantities and vector quantities. Scalar quantities are ones that don't have a direction. They only have a magnitude or a size. So this would be things like temperature, energy and speed. It would be meaningless to say 20 degrees C to the north. Vector quantities, on the other hand, still have a magnitude or a size, but they also include a direction. And these include velocity, momentum and forces. A vector quantity such as force can be represented by an arrow, where the length of the arrow represents the magnitude or the size of the vector, and the direction is represented by, well, the direction. This allows us to draw diagrams like this one, which is called a free body diagram. Basically, instead of drawing the whole object, I just do a little dot to represent the centre of it, and then I draw the arrows coming off there. All forces in the world can be split into contact and non-contact forces. Contact means touching, so a contact force is one that can only exist if the objects are touching each other. A non-contact force can exist even when objects don't touch each other, but that doesn't mean it goes away just because they are touching. You still have a weight, which is caused by gravity, even if you jump out of a plane, so this is a non-contact force. But we don't suddenly start describing weight as a contact force when you're stood on the ground. It can and does exist when you're not touching the earth, so we always describe it as a non-contact force. We've just named weight as an example of a non-contact force, but we also have electrostatic forces, which occur between objects with a positive and a negative charge, and you also know about magnetic force, which allows magnets to attract materials that are made out of iron or cobalt or nickel. Contact forces include friction, air resistance, tension, and normal contact force. Newton's third law tells us that for every action there is an equal and opposite reaction. This means that forces always come in pairs, and 4 things are always true about the pair of forces. The first one is that they are always equal in size. So if a book is lying on a table, then the book is pushing down on the table and the table is pushing back on the book, and the size of those 2 pushes is equal because otherwise the book would either fall through the table or it would somehow weirdly levitate. The second thing is that it's always the same type of force. So in that example, it's a push and a push. You're never going to have a push combined with a pull. The third thing is that they are opposite in direction. So the book is pushing down on the table and the table is pushing up on the book. And then finally, the forces are always acting on the other object. So it's the book pushing on the table, and that's the interaction pair is with the force where the table pushes back on the book. In everyday life, the words mass and weight are often incorrectly used interchangeably. When most people say weight, what they really mean is mass. Mass tells us how much matter or how many atoms an object is made from. So this square is made from 56 atoms. Mass is measured in kilograms, and the shorthand for that is kg. It isn't affected by forces. Your mass doesn't change because somebody pushes you or because you're experiencing air resistance. It also doesn't depend on where you are. So my dinosaur here has exactly the same mass whether he's on Earth or whether he's on the moon. Now, any object with mass that enters a gravitational field experiences a force called weight, and because it's a force, it must be measured in newtons. Gravity doesn't just affect planets or other really big objects like the moon, but the strength of a gravitational field is determined by the mass of an object. So Earth's gravity is about 10 to the 24 times bigger than yours, so you don't really notice that you have gravity, but you do. Now, this is important because the stronger gravity is, the larger of the weight that an object that experiences it will be. So in other words, if you're on the moon, you have a smaller weight than if you're on Earth because the gravitational pull of the moon is less strong than the gravitational pull of the Earth. And this is important because forces cause changes in motion. You've probably seen videos of astronauts jumping on the moon, and because their weight is small, because the gravitational field strength is smaller, they can jump higher and further. So to return to our earlier point about scalars and vectors, scalars don't have direction, so mass is an example of a scalar quantity, whereas vectors do, so weight is a vector quantity. Weight can be measured using a Newton meter, which contains a spring which stretches as a larger force is applied. This causes a marker to move, allowing us to read the size of the force. An object with a bigger mass also has a bigger weight, so it would trigger a bigger reading on the Newton meter. Weight and mass are directly proportional, so as mass doubles, weight doubles, and this means if we plot them both on a graph, we see a straight line which passes through the origin, 0, 0. You will have the equation sheet for the exam, but just remember that you are going to need to know the units for each of these quantities. Objects never have just one force acting on them, even though these forces may be invisible. When we're trying to explain all of the different forces acting, we can simplify these to make one resultant force. This makes it a lot easier to predict what's going to happen to the object's motion. In my example here, the 2 forces acting on the box are equal and opposite, so they cancel each other out, and so the resultant force acting on the box is 0, and it will behave as if there was no force acting on it at all. Sometimes the forces don't perfectly balance out, and it's a little bit more complicated. So here I've got a force of 60 newtons to the left and 100 newtons to the right. In other words, that force to the right is made up of 60 newtons that balances out the first 60 newtons and then an extra 40. So my resultant force is 40 newtons to the right. What that tells me is that my object will act as if I just had a single force of 40 newtons pushing to the right. Now, in order to explain how an object is going to move, we need a couple more of Newton's laws. So the first law tells us that when the resultant force on an object is 0, acceleration is 0. Now that doesn't necessarily mean that the object is not moving, it means that its speed and its velocity are not changing. So if it's already at rest, it will stay at rest and remain stationary, but if it's already moving, it will carry on moving in exactly the same way. Newton's second law tells me that the acceleration of an object is proportional to the resultant force acting on the object, and inversely proportional to the mass of the object. In other words, if I push an object twice as hard, it's going to accelerate twice as much, and if I push two objects equally hard, but one of them is twice as heavy, it will only accelerate by half as much. This all leads us on to the next equation, which is force is mass times acceleration. Again, you will have this equation on the equation sheet in the exam, but make sure you're comfortable with the units and make sure you remember that acceleration is a vector. So that means that you can have negative acceleration, which means that an object is slowing down. There's also a line in the specification about being able to estimate speeds and accelerations and forces involved in road transport. So it's worth going into the exam knowing that a mile an hour is about half a metre per second, because you probably know speed limits in miles per hour but not in metres per second. And also knowing that your average car weighs about 1,000 kilograms and your average lorry is about 40 times heavier than that. Work done comes up in paper 1 in the energy topic, but it's also here in the forces topic as well. Work is done when a force causes an object to move through a distance. So a force does work on an object when it's displaced. Again, you need to know your units for all of these different quantities. The next major topic is all about the motion of objects and how this links with forces, and we start with distance and displacement. Now, distance and displacement are both about moving away from a starting point and how far you get, but they are different to each other. Distance is a scalar quantity, so it doesn't have a direction. So you could think of this as you leave your house and how many steps do you take. Displacement is about how far away did you actually get. So you could think of it as how far did you go as the crow flies, or how long would it take you to get home. So to put this in context for you, imagine that we're starting out at the house at the bottom of the screen and we're trying to get to the house at the top of the screen. Now let's say that I went via the house on the right hand side. The distance would be 400 metres plus 400 metres. In other words, 800 metres, because that's how many steps I've taken. But the displacement would only be 400 metres, because that's how far I am away from my starting point. Likewise, speed and velocity are quite similar, but speed is a scalar quantity and velocity is a vector quantity, because velocity has a particular direction. So if I run at 5 metres per second due north, and then I turn around and run at 5 metres per second due south, my speed hasn't changed, it's still 5 metres per second. But my velocity has, because the direction has, and so I would be reporting my velocity here as minus 5 metres per second, because I'm running in the opposite direction. Now, depending on your perspective, speed is either a really good calculation or a really bad calculation, because unlike pretty much everything else in physics, although it does have SI units, we don't always use them. So what you would be expecting most of the time is that meters is going to be meters per second multiplied by seconds. But we could also have questions that are laid out in terms of, say, kilometers per hour, in which case we'd need different units. The important thing is that the units you're using for speed always have to match up with the units that you're using for distance and for time. You should know that typical walking speed is about 1.5 meters per second, typical running speed is more like 3 meters a second, and typical cycling speed is more like 6 meters per second. Also, sound in air travels at about 330 meters per second. In order to calculate acceleration, we look at how much velocity has changed over time. It may be necessary to work out what the change in velocity is from a final and initial velocity. So say I start out at 5 meters per second and I finish at 12 meters per second. So my change in velocity is 12 takes 5, which is 7 meters per second. And then I divide that by the time. Remember that acceleration is a vector, so it can also have a negative value because it's going in a particular direction. You should be familiar with two different types of motion graph, and it's important to know which one you're looking at. So make sure that you've looked at the y-axis and identified whether this is a distance time graph or a velocity time graph before you start. We can use distance time graphs to tell us about the motion of an object in both qualitative and quantitative terms. So if we ignore numbers to begin with and we just think about the general shape of the graph, on a dt graph, A horizontal line tells you that the object is stationary. So in this instance, the object has started out 3 kilometres away from the starting point, and then it's still 3 kilometres away. So it hasn't moved, it is stationary. If we look at this first bit of the graph, where it's diagonal, that tells you that the object is moving and that it has a constant speed or a constant velocity. If I now look at this bit here that is steeper, a steeper portion of the graph tells you that the object is moving faster. As I said, we can use these graphs for qualitative interpretation, but also quantitative. So we can use this graph to actually calculate what the speed would be. We know that speed is distance divided by time. So from the graph, we need to identify how much distance has the object moved through and how long did that take. So for instance, if I want to know what the speed is from C to D, I need to do distance divided by time. The distance travelled is 12 take 3 kilometres. So at the end, it's 12 kilometres away. At the start, it was 3. And then likewise, the time is 12 take 8 hours. So this would be 9 divided by 4, which would give me 2.25. And because my starting quantities have been measured in kilometres and in hours, my units for speed here should be in kilometres per hour. If the line on the graph is curving, then the object is not moving at a constant speed. And for the foundation tier, you're not expected to be able to draw tangents and calculate the gradient that way. But we can still take the starting and ending distances and times and use these to calculate a mean speed over that time period. As I mentioned, there are 2 different kinds of motion graph, and it's really important that before you start answering a question, you've identified whether you're looking at a dt graph or, like this one is, a vt graph, where on the y-axis we see velocity instead. If you're unsure, it's really worth reading off whatever is on the y-axis and saying things to yourself like, oh, at point B the velocity is 6 meters a second, and at point C the velocity is still 6 meters a second, because that's going to enable you to identify that between B and C the object isn't stationary, it's moving at a constant velocity. It's always moving at 6 meters per second. On a VT graph, if an object is stationary, then although it will be a horizontal line, that horizontal line must be along the x-axis where velocity is 0. If the line is sloping upwards, then this tells you that the object has positive acceleration, so it's speeding up. And if the line is sloping downwards, then it has negative acceleration, so it's slowing down. The steeper the graph is, the faster the acceleration is. You should also know that you can calculate the displacement of an object by calculating the area under the graph. It goes without saying that moving objects need some time and some distance in order to stop. If you've spent a lot of time on the motorway, then you'll be aware that lots of motorways have these white chevrons which are spaced 40 metres apart, and the idea is that cars should always have 2 of them between them. In other words, they should always be at least 80 metres behind the vehicle in front. Stopping distance is made up of 2 different components, called thinking distance and braking distance. Thinking distance is the distance travelled during the driver's reaction time, so not really while they're thinking about whether or not they want to stop, but during the amount of time that it takes for that signal to get to the brain and then get down to their foot. Then the braking distance is the distance travelled by the vehicle while it's under the braking force, so while the driver's foot is on the brake pedal, how long does it take the car to actually stop? Here are some typical thinking and braking distances for cars travelling at different speeds. As you can see, at 30 miles an hour, a car has a typical stopping distance in total of 23 metres, whereas by 70 miles an hour, it's more like 96 metres. Your reaction time is the time taken for a signal from your brain to reach your muscles, and it does vary from person to person from about 0.2 seconds to 0.9 seconds. You'll have measured this as part of the biology required practical in the homeostasis topic. It can be increased by tiredness, drugs, alcohol, and also just by being distracted. Thinking distance will be increased by anything which increases your reaction time. So we've already said tiredness, drugs, alcohol, and distractions. But thinking distance is also affected by the speed at which you're travelling, because the faster you're moving, the more distance your car will cover before the signal reaches your muscles in order for them to brake. The link between speed and thinking distance is directly proportional. So here you can see that at 30 miles an hour, there's a thinking distance of 9 metres, and then if we double that speed to 60 miles an hour, then the thinking distance becomes 18 metres, which is double 9. Because it's a directly proportional relationship, if we plot these 2 quantities on a graph, we get a straight line graph which passes through the origin, 0, 0. If we now look at braking distance, we can see that this isn't the case, and this isn't a directly proportional relationship. If I consider the braking distances at 30 miles an hour and 60 miles an hour, we can see that actually the braking distance at 60 miles an hour is nearly 4 times larger, even though the speed has only just doubled. So we can say that an increase in speed affects the braking distance much more than it affects the thinking distance. One reason for this is the amount of kinetic energy that the car has when it's moving that quickly. So if we take a car with a mass of 1,000 kilograms and we say that it's moving at a velocity of 10 meters per second, then it has 50,000 joules of kinetic energy, and it needs to lose that kinetic energy in order to come to a stop. But if I have the same car moving at a velocity of 20 meters a second, so twice as fast, then it actually has 4 times as much energy. So when we're trying to explain this, we can say that a car travelling at a faster speed or a faster velocity has more kinetic energy, so therefore more work has to be done in order to stop the car. And when a force is applied to the brakes, the work is done by the friction force between the brakes and the wheel. We can calculate the size of the work by looking at the force and the distance. Now, this also helps us to explain why braking at high speeds can be really dangerous, because it can lead the brakes to overheat. This is because the work done by the friction force, although it's reducing the kinetic energy, will raise the temperature of the brakes. And so if the braking force is too large, the brakes may overheat or the car may skid. We said already that travelling at a higher speed was going to affect the thinking distance, but it also affects the braking distance. As we've just seen, a car travelling at a higher speed has more kinetic energy, so more work needs to be done in order to bring it to a stop. So if we assume that the braking force is constant, then a longer distance is required in order to bring it to a stop. Additionally, braking distance is going to be affected by wet or icy weather. It's important that if this comes up in the exam that you're specifying the kind of weather and not just saying, oh, it's affected by weather, because that could mean a sunny day, which wouldn't affect it at all. Braking distance will also be increased by poor tyre or poor brake condition. So again, here it's important that you're being specific and not just saying the condition of the car. Unit 6 of Physics Paper 2 is the waves topic. We start out by saying that waves can either be transverse or longitudinal. The ripples on a water surface are an example of a transverse wave. Longitudinal waves, like this one here at the bottom, show areas of compression where the particles are close together and rarefaction where they're spread out. And sound waves travelling through air are an example of a longitudinal wave. You should be able to label a transverse wave to show peaks and troughs and wavelengths and amplitudes. So we start out with the undisturbed position or the equilibrium position, and onto that we can put our transverse wave. Remember, a transverse wave is one in which the oscillation is perpendicular to the direction that the wave is travelling. So my wave is going left to right, but my oscillation is going up and down. On this, I can label the peaks and also the troughs. So the peaks are all the highest points and the troughs are all the lowest points. And once I have these labelled, I can add in wavelengths. So the wavelength of a wave is the distance between two equivalent points on two adjacent waves. So I can go from peak to peak, but I can also go from trough to trough. You could technically go from one of the middle points of the wave, but it's really easy if you do that to actually accidentally only label half the wave, so I wouldn't recommend doing it. The one that people tend to get wrong is the amplitude. So remember that the amplitude is half the height of the wave. It's the maximum displacement of the wave from the undisturbed position. The other thing that you need to be able to identify is the frequency of a wave. So if this box represents 1 second, then there are 3 waves inside it. In other words, 3 waves have passed a point within a second. So the frequency is 3 Hertz. Linked to this is the period. So the period is the time taken for one wave. So if I've managed to fit 3 waves into 1 second, then the period is going to be 1 divided by 3. In other words, a third of a second. Again, we have another calculation, so just make sure that you're familiar with all of the units for all of the different quantities. Electromagnetic waves are transverse waves that transfer energy from the source of the waves to an absorber. All types of EM wave travel at the same velocity through a vacuum or through air. Electromagnetic waves form a continuous spectrum. In other words, there isn't something fundamentally different about a radio wave and an infrared wave. It's just that we give them slightly different names depending on their particular frequency and wavelength. So you can think of it a bit like how in a rainbow, there isn't one set point where red turns into orange, we just give it a slightly different name depending on its wavelength. Going from long to short wavelength or low to high frequency, the groups of waves are radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays and gamma rays. Within that visible light portion, we start with red wavelengths, which are the longer wavelengths, so you can think that infrared goes next to red, and then we finish up with violet colours next to ultraviolet. Our eyes only detect visible light, so we only detect a limited range of those electromagnetic waves. The one required practical that's been named in the advanced information for this paper is about investigating how the amount of infrared radiation that is absorbed or radiated by a surface depends on the nature of that surface. So that could be something like, is it shiny or matte, or does the colour make a difference? So in order to test this, you're going to need a number of identical cans or hollow metal cubes. They need to have the same dimensions but different surfaces. So the surface that we're changing, say the colour, that's your independent variable, and we want everything else to be the same because otherwise we don't know whether it's the colour that's affecting it or whether it's something else. You fill the cans with hot water from the same kettle so it's starting at the same temperature, and then you use a ruler to position an infrared detector at a consistent distance away from the can. So you don't want to have one situation where your infrared detector is 10 centimetres away and then for a different can it's 20 centimetres away, because that way you wouldn't get valid data. Then you use that infrared detector in order to take readings. You can also take the temperature as a surrogate for this, but the data just isn't as valid. Electromagnetic waves are really useful, and you need to know what each portion of the spectrum is used for. So radio waves are used for both television and radio broadcasting. Microwaves can be used for satellite communications like sending text messages, but also for cooking food in a microwave oven. Infrared radiation is used in electrical heaters, but also to cook food, and also in infrared cameras which can detect body heat for things like manhunts in the dark when the police are chasing someone. Visible light is used in fibre optic communication like broadband. Ultraviolet light is used in energy efficient lamps, but also in suntan beds. And then X-rays and gamma rays are used in medical imaging and also in treatments such as radiotherapy. The final topic in physics paper 2 is the magnetism and electromagnetism topic. We start off by saying that the poles of a magnet are the places where the magnetic forces are strongest. When you bring two magnets together, they exert a force on each other. So if you're bringing together the like poles, like north and north, then they will repel each other. Whereas if you bring together the unlike poles, such as north and south, then they will attract each other. This attraction or repulsion is an example of a non-contact force, as we discussed in Unit 5, the forces topic. A permanent magnet, like this bar magnet here, produces its own magnetic field, and we can visualise this by using a plotting compass. The idea is that you move the plotting compass around the magnet and you sort of do a little dot to show which way the arrow is pointing, and it's always going to be pointing to the south pole, and then you can then join up your dots in order to draw the magnetic field lines. An induced magnet is a material that becomes a magnet when it's placed in a magnetic field. So you can think of this like where you do the electromagnetism required practical and you're picking up paper clips, and actually the paper clips don't need to be touching the electromagnet. If they're touching another paper clip, then there's still that magnetic attraction there. So the thing with induced magnetism is that it always causes a force of attraction, it's never repulsion, and also if you take the object out of the magnetic field, then it very quickly loses most or all of its magnetism. So that magnetised paperclip, if you take it off the electromagnet, it's not then able to pick up other paper clips just on its own. So we've already said that the area around a magnet where a force is acting on another magnet or on a magnetic material is called the magnetic field. Those magnetic materials are iron, cobalt and nickel, and also the exam board mentioned steel, which is an alloy made of iron, so that's why it's magnetic. Where you've got a magnetic material, so say a lump of iron, rather than a magnet, the force acting on it is always going to be attraction. So whereas one magnet can repel a different magnet, if we're trying to put north and north pole together, if we've got a magnetic material like iron, it's always going to be attracted. How much it's attracted, in other words, the strength of that magnetic field, is going to depend on the distance from the magnet. So if it's further away from the magnet, it experiences less attraction. That's just kind of obvious. And also the attraction is strongest at the pole of the magnet, which I think we have actually already said. If we're trying to work out what the direction of the magnetic field is, then we need to find out what would be the direction of the force if we acted on another north pole. So basically we take the north pole of a magnet and we see which way is it being orientated. So that's where you need one of those little plotting compasses which has a small bar magnet in it, and we see which way does the north pole point. Now the Earth also has a magnetic field, so the compass needle in a plotting compass will point in that direction as well. And this is how we know that the place that geographically we call the North Pole is actually, magnetically speaking, a South Pole. Then we get into the electromagnetism bit. So when a current flows through a conducting wire, a magnetic field is produced around the wire, and you can use your right hand rule in order to tell you what the direction of the magnetic field would be. So if you give a sort of thumbs up sign with your right hand, then your thumb is showing the direction of the current in the wire and your fingers are showing the magnetic field. Now, the strength of that magnetic field is going to depend on both the current that goes through the wire, so if a bigger current flows, then the magnetic field gets stronger, and also the distance from the wire. So just like with a regular magnet, the closer you are to the thing generating the magnetic field, the more attraction you experience. If we shape that wire to make a solenoid, in other words, a hollow coil, then that's going to increase the strength of the magnetic field. And the magnetic field inside that solenoid is strong and it's uniform, so it's all the same. The magnetic field around the solenoid has a similar shape to that of a bar magnet, so you would just draw it in the same way. If we add in an iron core, then that increases the strength of the magnetic field again, and this is what we call an electromagnet. So that's it for the foundation tier of Physics Paper 2 of AQA Combined Science. I really hope that you're feeling a bit more confident about this, your final GCSE Science exam. I'm wishing you lots of luck for tomorrow, so I really hope that you can just go in there and do your absolute best.